everyone, welcome to my channel. Today I have picked shaping rainwater problem from top interview 150 problem series. I am exactly going to tell you how you have to explain this problem in the interview. This is a very important problem from the interview point of view. So please focus properly, and I am going to explain brute force to optimal approach here. First, let's understand the problem. Before understanding, there are few things I would like to tell you. That you see here we are given some constraints. So what these constraints means, we are given n, which says that n length, so n is the length of the array, is going to be between 1 to 20,000 around. The value of height not exceed more than 10 to the power 5. There are few problems that are hard. Initially you won't understand what approach you have to apply, so you can just refer to these topics. Let's understand the problem here. Simply you just have to know that you are given some sort of structure, and in that structure how much water it can contain, you just have to compute that. The only issue here is that suppose there is going to be some area where you have to compute the water. We are given the heights array. In the heights array there are given some heights, so based on what, whenever these heights are coming, these heights are like blocks, so we have to avoid these blocks while computing total water. So let's quickly move towards the solution. Before discussing the solution, I'd like to give you some real life example, and you have to be very interactive, or you just have to imagine what I'm trying to say, okay, while I am explaining. Imagine that you are given a glass, okay, and you just have to compute how much water it contains, but the glass has this sort of structure where the one side the height of the glass is like this, and at one side the height of the glass or container, whatever you say, is like this. So suppose you start pouring water into it, so what would happen? Initially the water would get filled at this point. After that, if you try to pour inside it, what will happen? The water will overflow, right? So what would you say, how much water it can contain? This much, okay. Even though the height is different, like here the height is somewhat this, and here the height is somewhat this. So on what basis you are going to compute water value? On the basis of minimum height out of those two, right? Not the bigger one, but the smaller one is going to decide how much water it is going to contain. Now I would ask every one of you to just try some different figures on your notebook, and then decide how much water it can contain. Let's tweak this example a bit now, and suppose you have this much water, and suppose you have this this container has some sort of structure in which this much space is blocked, like this is a solid space. Now how much water you would have? You would say that the area of this container, like height of this container, width of this container, is going to be like volume or whatever you say, that this area is going to be containing the water minus this area, right? So this is the second concept. What we have done till now, what we have done, first thing is that we maintained minimum height, okay. And now second thing is that whatever area we have of water minus blockage, okay, block. Now let's take a bigger picture, okay, and please concentrate very carefully, because if you understand what I am trying to say right now, then you will never be confused with this problem, okay. Suppose we have some sort of heights given, okay. Now you start pouring into these heights. Suppose this one, so this one, it will get poured till here, okay, and then it will stop. Let me do changes here, some sort of, let me do some change here. So here, see, so it will start pouring in, and it will stop at this point, because water will start getting out of this. So ideally the left one can stop here, but if you see here, stop at we can stop at till this point, and in this case as well we will stop at this point. So what we can say, at any side, like if you compare a smaller container, left, this is the, for this container this is the left and this is the right. For this container this was the left one and this was the right one, so minimum of left and right we took, right? But if we look at the bigger picture, then we have to consider from any side the maximum one. Here if we start pouring from the leftmost, then we will consider this this maximum one. And if we start pouring from rightmost, then we will consider rightMax. Okay, so just conclude this, what we do that at any point, if we compare, we take leftMax from the left and rightMax from the left, and then we take the minimum of that. Like this example, you see, we compute the minimum for the actual results. But in this case, you see, why do we take, and now the question is, why I am taking the maximum? I am taking the maximum because because in the left, if I consider this block, then only we say we have to stop here. But my left, this one has the, in the left side, this one had the bigger height, so obviously we have scope of more water to fill into inside this, right? So we will not consider this left, but this one from the left. And since the right one, you see, but if we compare from the right, this one has the bigger height and this left has the smaller height, so we will take this, because if we, even if we try to pour water will not get stored inside, but it will get poured outside like this. So the kind of slope, you see, this decides that how much water it contains. So just to conclude, from any side we take the minimum of, if we compare to left and right, then we take minimum, and if we choose just one side, then we take maximum. Okay, so in on that basis, we came to the conclusion that at any point, and or remember I explained the example earlier, that what these heights mean. So suppose there are blocks like this, okay, so in suppose, and all this is water, all this is water, all this is water, then we are going to ignore these blocks, because on these blocks water is not present. In this case, we will compute the whole area, and all at any point we subtract whatever height we are having right now. So this is the only conclusion of what I am trying to say here. This is the conclusion, that at any point we compute left max, right max, and then we compute minimum of that. At any point, if you get any question that why are we computing minimum, we are computing minimum because water will get poured if we don't take the minimum. Okay, poured outside. And we take the left max because there is some scope of water getting stored in at any side, and we are subtracting height at every point because these are the blocks that are given. See, this is the only conclusion that we have. Now let's quickly see, we in the interview you are going to approach first the brute force. So this is the only conclusion, that we keep on taking highest bar from the left, highest bar from the right, like this, highest bar from the left, highest bar from the right, and water trapped at that index is going to get computed at left max, minimum of left max and right max, and minus of height. But what happens in the brute force, that at every point we have to compute, you are here, so you will compute the maximum right, you will compute the maximum left and subtract the height. Okay, so this is going to take enough square time, because at every point we are computing left max, right max, and then we are doing all the computation. By now you all must have understood what optimal approach we are going to use, what pattern to use. If not, I would urge all of you to take a pause and then think about it, what approach you can use here. For computation, at every point we are going to do this, but using two pointer. So see how we are going to use two pointer. We are going to maintain a left pointer, right pointer, okay, left max, right max. So quickly see how we are going to do. Pattern is two pointer and pointer movement is inward. Okay, so left, initially we will start from here, left, and right will be here. It will start, it will shrink inward. At every point it will compare whether my current height is smaller or bigger. If this current height is, we don't have a smaller, at left we don't have a smaller, it will just compute the water. And there is no block, so it will just ignore. It will come here, it will check. So at this point, you see current left is greater than left max, so this left max is going to get updated. It is going to be minimum of left and right. You don't have to forget. How we are going to maintain is that we, at every point we are going to check whether, if my, like minimum, you see this is the summary of minimum of left and right. This block is for left and this block is for right, and this is how we are comparing minimum of left and right. So in now again, and how we are going to maintaining max, we don't have to update maximum from both ends at every point. We just have to take which side has the minimum value and then keep updating the maximum from that point only. Here the left max is going to get updated, and in the next iteration it will come here, it will check, okay, now it has some water, it has some height, the height is lesser than the earlier height, so left max is not going to get updated, but the water is going to get computed. It will come here, now it will add some water, it will come here, add some water, subtract the height. At this point, suppose if my left is this and the right is this, so now you see right max is minimum than left max, so now right pointer will move inward. Suppose my right pointer is here, it will compute water, it will come here, and this is how we are going to work around this. You can compute this simulation on your own. The summarized version of this is that we are going to maintain two pointer to compute this, and at every point we are going to update whatever side we have chosen, we are going to update left max and right max accordingly, and this is how we are going to compute the mean. Let's quickly code this one. We'll be having two pointers, left is equals to 0 and then right will height of length minus 1. Okay, we will have left max, we will assume my left max is height of 0. I will have a right max equals to height of and obviously we will have some water. Now while in the two pointer we do like that, okay, if this is how we do this is how we do minimum of left max and right max. So current, if my height of L is less than height of R, we will come in this block. This is the very important point I am trying to say here, that you see we know that we have started from left and right. At this point we don't have to compute water because this is the boundary, where in every scenario you see we update the pointers in the end, but here we update the pointer in the starting only. And also we now next we have to compute if my left max is greater than the current height. If that is the case, then we update the left max, and also we will compute water. If you do the simulation now, you will understand what I'm trying to say. Left max, this is the, suppose you are here at this point and then you have this left max, then what is going to get computed? Left max minus height. So this is the case, height of L. Now we are going to do the similar approach for else as well, just reverted values. Suppose this is at the right, in the example I explain how we are computing on the right side. So we are taking it and then we are doing it. If you don't understand, please go through the video just more than one time, then you will understand what I'm trying to say here. How we are going to check, how we are going to shift sides from left, and then we will shift sides from right. Okay, so now in the end we will have a water, maximum water, then we will just return water. Okay, I have done a typo, which I always do, don't be like me. So accepted, submit. This is submitted as well. The time complexity is going to be big of n, and this is the code, this is the notes. Thank you.